the probability of and in that if we have two events, right? You know, we call them events A and events B mostly. We have seen the probability, okay, of events A and B occurring, right? What about or? You know, what about the probability of A or event B occurring? That's where this comes in. Okay? That's where this comes in. Basically for or, okay, the probability of that, we have this equation. We have the probability of A plus the probability of B, and then we subtract the probability of A and B occurring. And the first example I'm going to do actually illustrates why we have to subtract, which I also wrote here. Basically, if you don't subtract this, you might be counting certain outcomes. You might be overcounting certain outcomes. That's better. You know, you might be counting them more than once, which you should not be doing. That's why we have to subtract this. I was going to say, oh, okay. Also, let me just say this. I know I wrote or both here. Here, we're regarding or as the math or. In other words, mathematically, when you say or, you allow the possibility of both. So it's not like when you're talking to your friend or something and they ask you, you know, where do you want to go for lunch? Do you want to go to, I don't know, McDonald's or another place, Moe's, let's say. You know, in town, I mean, Oneonta. Do you want to go to McDonald's or Moe's to get lunch? Well, usually when they say or, they're not implying let's go to both, right? But mathematically, both is a possibility when you say or. So when you say event A or B occurring, you are taking into account both occurring, but we do subtract this to avoid overcounting. Because what's in here will be counted already by the sum. You don't want to count it more than once. So that's why we subtract. Okay. Well, let's do an example of this. So this is actually what was I going to say? I think one of the first examples we did. You know, we flip with events being independent. So here we're going to flip a coin and we're going to roll a die. We're going to look for the probability that the coin lands heads up, or we're going to roll a 6 on the die. Okay, now first, what I'm doing is I'm solving that by just looking at the sample space. I mean, what's nice here is that the sample space is not that big, right? It's only 12 outcomes here. That's not too bad. Okay, so if we flip a coin or roll a die, we want the outcomes, right, where either one of those events happens. Okay, so we flip a coin, and the coin lands heads up. We want that. Well, that's all these, right? So these have to be included. So that's in here. But we want to make sure, we want to consider the event where we're rolling 6. Where does that occur? Well, that occurs with this outcome. We get a 6. It also occurs with this outcome. So we have to add those in there, although this is already in there, right? We don't add it again. Hence, overcounting, we want to prevent that. But we have to throw this one in here because we get a 6 there. All right, how many outcomes are there? There's 7, right? So the probability here of flipping a coin and the coin landing on heads or rolling a 6 on the die is 7 over 12. Notice if we allowed repetition, so to say, from the coin, we would have the first 6 outcomes. From the event of the coin landing heads up. From the die rolling a 6, we would have H6 and T6. But H6 is accounted for already. That's actually both events occurring, right? And we were careful not to list that twice. You have to watch out for overcounting. Okay, now that's one way of doing this, so to say. Let's now consider that formula. So in other words, we're going to look at it from another viewpoint. I know it's kind of silly because I have the sample space again, but I do want to illustrate the formula. Okay? In other words, we could have just solved this by looking at the sample space and boom, we're done. But let's also solve it using the formula. Okay, so here I'm just illustrating really what I said in words, right? For instance, for event A, where the coin lands heads up, right? That's all these outcomes. And there are 6 of them, right? That's what the probability of this event is, this. Okay, for event B to occur, right? That's where you roll a 6 on the die. But as I said already, that's these two. That's these two. So the probability of B is 1 over 6. Excuse me, 2 over 12, which is the same as 1 over 6. And this is what I was really saying on the other slide, right? If we just added these without thinking, H6 would be counted twice. H6 is in both events. We don't want to count that twice. So to account for that, we have to subtract H6. In other words, we have to subtract off the probability of both events occurring. Both events correspond to H6. So that's why we're subtracting. That's all I'm just trying to illustrate. I'm just trying to give an idea why you subtract. But I figured it wouldn't hurt to do that. All right. Notice also these two events had something in common, right? You could have the coin land heads up and roll a 6, right? That's possible. That could definitely happen. In other words, A intersect B, the probability of this was not 0. That brings us to the next definition, of which A and B here are not mutually exclusive. So basically, two events are mutually exclusive if they both cannot occur at the same time. For the previous example, they were not mutually exclusive. But if they're mutually exclusive, well, if they can't occur at the same time, right? Then we have this. The probability is 0. They have nothing in common. They have no outcomes, so it's impossible for both to occur. And what's nice about this, as you can see, right, is that if they are mutually exclusive, you can get the probability of A or B just by adding. Okay? You can get that by adding. It's easy. You don't have to worry about overcounting because there's nothing to overcount. That makes sense. I hope it does. Okay, that's good. All right, well, that was one example. Let's try another one for fun. So again, we have that deck of cards, right? And as before, we're drawing cards at random. Okay, so in this case, we're only going to draw one card. We want the probability the card we draw is an ace or a card from the suit of clubs. Okay, now, so we're going to let A be the event. The card we get is an ace. Okay? B is the event. The card is from the suit of clubs. Well, how many aces are there? There's 4. There's 4 aces, so the probability of event A occurring is 4 out of 52. For the suit of clubs, we know each suit has 13 cards. The probability of B then is 13 out of 52. Now, how many aces? Now, about both, we have to consider that. Well, there is an ace that has a suit of clubs, right? In fact, there's only one. These events are not mutually exclusive. In other words, the probability of both A and B occurring is 1. 1 out of 52. Because again, there's only one ace from the suit of clubs. So going back to that formula, we have this, as you can see. We have the sum minus what's in both. Remember, when you have a common denominator, you just add or subtract the numerators. But just basic fractions, okay? So we have 4 plus 13 minus 1. What is that? That's 16 out of 52. So that's an example.